Right. So let's see. So what did we do last time? Um, so if you go back, um, we did this dipole approximation, okay, which was one of the things that we worked out for a number of charges. When there's not one single charge which is radiating, but there's a bunch of charges around, and so we can approximate by the dipole approximation. And of course, we also showed that what happens in the generalization for multipole. Now, of course, generalizations are good, but even with the dipole approximation, there is a lot of important physics that we can do. So the first thing that we want to do today is an application of dipole approximation, and something that you have done, I guess, many times. So this is something which is not completely unknown, but I think she is probably familiar to all of you. So we are going to look at, and there it is, one quick application of the dipole approximation. Okay, so look at an application. Of dipole radiation, which is basically Thomson scattering. Okay. Scattering. So basically scattering by an electron. There's an incident EM wave, and how does that EM wave scatters from the electron. So that's the application. It's an important application of the dipole radiation. So what is Thomson scattering? It is the free charge. It is in response to an incident electric wave. So how does free charge scatters? Basically responds to some incident EM wave. Okay. And so let's say there is some there is an EM wave which is going like this. Matter. Okay. There is a charge over here. So because the EM wave is going, it oscillates. Okay. It oscillates. Okay, there is a charge. And so the EM wave is polarized. So this is the direction, let's say. That's how it's going. So how the electric field is going up and down. Okay. And then there's a scattering. And this is in cap, of course, this like this. And let's say this angle is some whatever, some large theta capital. So that's the basic idea. Okay. And basically from now, this confusion arises. Sometimes I write Q, sometimes I write E, but basically charge electron is charge E. So if you sometimes if you see there is making sometimes while writing Q, I should have written E. Just correct it yourself or tell me that it should be Q or it should be, doesn't matter. Okay. So what we have is a linearly polarized EM wave, the force, okay, which is on that electron is from linearly polarized EM wave. This is an important word, linearly polarized, okay. And so your force basically you have a polarization, epsilon, and then E, 0, not T. Okay. And so I can write down the force equation over here very simply. I can write down M, so the force equation. So I can write down M or double dot is equal to. And if I define the dipole moment, so the dipole moment. Okay, the electron dipole moment. So over here, of course, instead of Q, I have written E because it's an electron. Doesn't matter. Okay, electron dipole moment, that D is equal to E times R. So don't you write the electron dipole moment, that I can solve this equation, and I can write down the double derivative because there's an R double dot, so automatically you get a D double dot. It's basically E squared 0 by M. T. Okay. And you integrate this. This will give you your.
Sir,
Miss Nikhil?
here we are assuming the some model of the electron, right?
Over here is electron, till now is just a point particle.
So since it's a point particle, that the force cannot act at every time, right? It will act only when the amplitude matches, and the amplitude just pass through that.
You know, the point particle electron has the problem, and we will come to that in a today class itself. Okay, so at present is just a classical electron. You will see very soon I will go out of the, I mean, you cannot go out of the classical electron in an ED course, first of all. Okay, so I will never go out of the really classical electron the way the electron should really be treated. And it will always have this kind of questions or problems that we'll talk about, but we are going to do hand waving ways, pre-quantum mechanics, PQED treatment of all these things. And so at present is a point particle. Very quickly we'll define some, not a point particle, but the classical electron radius will come in, and all these things will come in. Then we will see that will also have a problem. So yeah, your questions are right, but this is all done in a very, very simplified way. Well, not I wouldn't say it's a simplified, but I mean, these things work. I mean, in the sense like it's not only in some cases you will find problems, because we basically do Thomson scattering. The formulas that you get is it's practical formula that you use. So it's not that it's wrong completely. But your doubt is true. I mean, there are problems. So this will give you E squared, E0, then M omega naught squared, then this whole thing. Then there's an 7 sine omega naught. Okay. So this is basically the oscillating dipole amplitude D0. So this thing is the oscillating dipole amplitude. You can call it DC. Okay, so now when you have a dipole and there is dipole amplitude and you know D double dot, then we have already written down the equations for dipole radiation. Okay, so remember, so you have power radiated in a solid angle dpt omega was D double dot squared over 4 pi c cubed sine squared theta. This is the angle between the two the polarization direction and the scattering direction. So this was there, and then of course the total power, the very famous the Larmor formula, was basically again 2 D double dot squared over 3 C. So now what we can do is that we can use this in this above equation for the scattered radiation, and we can write the time average power. So now using this, we can write the time averaged power. Now, when you do the time averaging of this equation, the this dipole equation, remember this sine omega t, that sine squared omega t, that will give you the averaging of sine squared omega t will give you a half. Okay, so averaging of sine squared omega naught t, this will give you a half. And so this equation now, what we'll get is, therefore, dp d omega will give you, so I've written e, right? Yeah, e to the power 4 e0 squared by 8 pi m squared c cubed sine squared theta. So this theta should be vector theta, and your p will be e4 e0 squared 3 m squared. So this is what we get for the scattered radiation. Now, the important thing is to connect this to the cross section. Okay. So first, note that if I have an incident flux,
Sir,
yes,
sir, in 1 or 2 minutes ago, what Nikhil was asked that the dipole, if we treat electron as a point particle, then what should be the meaning of the dipole actually here? So here, can we say this thing like that? That here we are putting when we integrate the mechanical equation, that is d double dot equals to e square e0 sine omega t. Then if we integrate it twice, then we will have a d0. We'll have two integral constants. One is d1 and one is d0. Then we are putting d0 equals to 0. That means if we don't put an electric field, then the dipole have a zero length. But if we put an electric field only, then it will start to behave like a dipole.
see over here when I talk about a dipole, this is sort of an averaged kind of thing, you know. It's not really instantaneous as Nikhil was saying. So look at this figure. The R, so if you have some electron oscillating, electron is going like this, oscillating like this.
Yeah. That I just want to mean that existence of dipole is only is present only the electric field is applied. Until and unless the electric field
Yes.
is applied, it will just behave like a point particle.
Exactly. Yes, that's true.
Okay.
Okay, so where I was, yeah, so incident flux. So the incident flux, your S, the pointing, is basically C by 4 pi times, no, C by 8 pi times E0 squared. Okay. So remember this. Now, the way I define a cross section is that you have some incident flux, and cross section of scattering basically takes this incident flux and by multiplying by this cross section gives you the outgoing flux. That's the basic definition of cross section, right? If you have some particles coming in, some incident flux coming in, this entity, whatever, has some property such that this thing hits you and it goes somewhere else. And that is very roughly the cross section, the very rough view of cross section. So you have an incident flux, and cross section processes that incident flux into an outgoing flux. So if I think of it in that way, then I can define a differential cross section. So I can define, a differential cross section d sigma, okay, for scattering into solid angle d omega. So it comes and is scattered into some solid angle d omega. So I can write down dp d omega. Okay, remember this is the outgoing flux. Okay. dp d omega is basically my send flux into d sigma d omega. Okay, so this is out, this is in, and this is the cross section. Okay. So dp d omega, this thing is basically c by 8 pi E0 squared d sigma d omega. So therefore, I can write down the cross section for Thomson scattering. Therefore, my d sigma d omega is, and let me actually write down polarized over here, because the incident radiation was polarized. The outgoing radiation is also polarized. Both are linearly polarized. Remember that. That is this divided by c by 8 by E0 squared. So E4 the m squared C4. So it is E4 by m squared C4 sin squared. So this is the cross section. This is a differential cross section for Thomson scattering. It's an important quantity, and it's very much used in particle physics, okay, wherever there is a electron scattering. Now, remember, although the electron is a point particle classically, over here I have, in a sense, come to a quantity which I can write down as R0 squared, and this thing I can write down as R. I can write down this thing as R0 squared sin squared theta, where this R0, where this R0 I define as E squared by MC squared. Okay. Now, why do I define E squared by MC squared as R0? R0, of course, is some length scale. Okay. So as you can see, this is like, so if I write down my MC squared, so if I write this slightly differently, so the reason this is R0 is that my energy, okay, which is MC squared, is equal to E squared by R0. So this is like the self energy of the electron, okay? And I can think of the self energy as the potential of the electron in which the potential electron is residing. So it's a very vague way of saying though. And that potential energy is your self energy of the electron. So that's why the scale R0 comes over here. Okay. And so,
sir?
Yeah.
Sir, why we are so much interested to write the d sigma d omega in a R0 square sin square theta this form? If we write this in form, then we can attribute a meaning to R0.
We are not interested in writing in, but first of all, there are two things. First of all, d sigma, your cross section is whatever it is. You see, this is your cross. So let me get rid of. I can't get rid of. Okay, I can put my hand over here. What you can see. Just think in the box. That is your cross section. Okay, so there is no R0 over here, but cross section, by definition, but the standard way of thinking of cross section is an area, right, that something presents to an incident wave or incident particle. So whatever you do, whether you do any type of scattering, cross section is an effective area. An effective area is always some radius squared, right?
Okay, involve a square of a length scale. Yeah.
So that's right. But then when I put in the effective radius, that radius is E squared by mc squared, which is like, in a sense, the radius of an electron. Now, this is a classical electron. No, so radius of an electron doesn't make sense over here, but you see, I've done it very vaguely. I think of the energy, and energy is like this energy. What is the self energy of that electron? The mc squared. Okay, that I can think of the potential of the electron, which is E by R times the charge of the electron, which is E squared by R. That gives you a scale. Okay, so now instead of a point particle, you can think of R0 as some size of the point charge. It is not a very good definition, but this gives you this is kind of transition between the classical picture and later when you think of the electron in a slightly quantum mechanical picture. So what is R0? It's like so this R0, it is like some size of the point charge. No, point charge, of course, has sizes, but I'm talking about size. And this mc squared is of electromagnetic origin over here, because mc squared is E squared by R, right? So this, its rest mass, okay, which is mc squared over here, is of electromagnetic origin. That's it. So I can put in numbers over here. Okay. So if you look at the classical electron, so for the classical electron, which is basically an electron without any quantum mechanics in it, so for the classical electron, my R0 is typically 2.83 10 to the power minus 13 centimeter. So one of the things why this is important is this also tells you later typical scales in which our classical treatments will fail. So if we are talking about some physics which are 10 to the power minus 12 centimeter, then this is fine. So our classical, the EM theory that we're doing for the electron, this classical EM theory, that will be fine. So if you think of length scales which are oscillating, this will be fine. But if you're trying to do EM theory in a region, a classical EM theory in a region which is of this order or smaller, then obviously our classical definitions will fail. And so you'll see a lot of the fallacies. And if I have time next day, I think I was thinking of doing, I didn't do it last time. Think of doing some of the fallacies, and you'll see one of the reasons is because this fact that we go to length scales where this length scales become very much like this, and then you can compare with some other length scale, let's say Compton length scale, and you have to see which length scale wins over and what is happening. So this is one length scale to be aware of. Okay. By the way, so once you have this, I can integrate this to get total cross section. So the total cross section I can also write. Section Thomson total Thomson cross section sigma. Okay, this sigma d omega, and this is basically 8 pi by 3 R0 squared. So again, this is an important relation, often used. Okay. And this is basically 6.6. This is an important number to keep in mind. 10 to the power minus 25 centimeter square. So for electron scattering, this is the most important number. If your beam is much larger than this number, this area, then the scattering will be very less. So you must have a beam which can probe an area like this per electron, of course, to have an electron scattering. So this is something that you should keep in mind. Now, if you look at this number and this cross section, there are a few things that you should keep in mind. So let us write down a few things. Okay, so first points to remember is this. Points to remember. First is that the cross section, the d sigma, d omega, or the sigma, that does not depend on the frequency. Okay, so your d sigma, d omega, or sigma are frequency independent. Okay. Frequency. Of course, again, this is valid for low frequencies. So what? Low frequencies. So classical, not very high frequencies. Okay. Why is it for low frequencies? Because if you go to high frequency, okay, then the energy of the photon itself can be equal or more than the energy of the electrons. Okay. So then this kind of treatment will not hold. This is a classical treatment. So at high frequency, your h nu can be greater than or equal to mc squared. And so we have to do QM treatment. So this is something that if I have time, I will, even then I will not be able to do it probably in full general details. So this is a classic case, what happens when you have X-ray radiation. The X-ray radiation, you do the same thing, but over there, the energy of the photon is greater. And so you cannot do it this simply, so you have to make corrections to that. And we'll try to do it if I have time. At least try to tell you the kind of parameter dependencies or kind of form that X-rays should have. People who work in astrophysics or cosmology, X-rays are a very important probe of the universe. And the reason is that when you get some X-ray radiation from some point, you see that it tells us about the temperature and the density of that region. Okay. And what I will try to show you that the density dependence is like n squared, the temperature dependence is like t to the power half. You can do those things later if you have time to do it. So this is one thing. Also, okay, then there is polarization. Okay. Yeah. That's another basically thing is that all these things was done in non-relativistic. So the incident radiation should not be very large, or the electrons will oscillate relativistically. So then our, so we have to be careful that the incident radiation should not be too large. So electrons are always non-relativistic. And finally, which was something that I said, that the scattered radiation is also linearly polarized. So scattered radiation is also linearly polarized, okay, in some n-cap direction, where the incident radiation was linearly polarized. Now the funny thing happens when we move from this linearly polarized incident radiation to an unpolarized radiation. So over here, when you remember when I drew the figure over here, we had a linearly polarized incident radiation, and it scattered, and there was a linearly polarized scattered radiation. What happens if the incident radiation is not linearly polarized? Okay, So what happens if I have an unpolarized incident radiation? That's also something as interesting extension that one should look at. So let us look at what happens for unpolarized incident radiation. Now to do this, we're going to do a trick. When I think of unpolarized, the easiest way to have an unpolarized radiation is to superpose two polarized radiation. Okay. So we superpose two polarized radiation at perpendicular axis. So polarization at two polarization is perpendicular axis. And if they are the same strength, you can give you a final result which is unpolarized. So that's what we're going to use, the trick. So your unpolarized radiation, I hope you can understand what I'm writing. Sometimes the writing is becoming very bad. The unpolarized radiation, okay, incident. This is basically superposition of two linear polarized radiation. Okay, they're all incident beam, by the way. Okay, with perpendicular directions. So I can draw the same picture that I drew before, this one, slightly separately. So let us look at this picture. I draw two pictures. So now I have another polarization, which is, let's say, perpendicular to this direction. So it will be out the plane of this of the blackboard of the paper. So now I will have something like this. Okay. So remember, initial polarization was in this direction, epsilon 1. This is how it was going. So this is the direction. Okay. This is epsilon 1. And let's say this is your incident direction. So K cap. And remember, your thing was N cap was the outgoing radiation. And this angle was big theta. Let me call this angle as small theta. And then perpendicular to this, there will be another polarization direction, which will be, so it should be like this. Okay. This will be, so this is E1, this is epsilon 2. And the idea is this epsilon 2 is 90 degrees to this plane. So this angle, right, this angle is pi by 2. Okay. So epsilon 1 is equal to polarization of first beam, epsilon 2 polarization of second beam, Z is incident direction, and cap is outgoing direction, scattered direction. Okay. So now, so this is what you, okay. So now angles, of course, is the angle between the incident direction and scattered direction is theta. The angle between the epsilon 2 and the scattered direction is pi by 2 as a. And also just one thing, remember your theta, this theta is basically pi by 2 minus the theta. So given this, if I want to write down the cross section, I will just take the average of the two cross sections, right? So differential cross section is unpolarized. So now, okay, so your cross section, so your d sigma d omega unpolarized is equal to average of polarized d sigma d omega. So therefore your d sigma d omega unpolarized is the average, so just half because there are only two of them. Okay. So remember, first one is d sigma with theta d omega. This is polarized plus d sigma d omega, and this is theta is pi by 2. This is again polarized. That's it. It's as simple as this. So now look at this figure and you will see that this is what it is. So in one case, the angle between the incident polarization, the incident epsilon 1 and n was theta. In the other case, it was epsilon 2 and the n cap was pi by 2. So we're writing pi by 2. Okay. Now, also remember that your this capital theta is equal to pi by 2. Pi by 2 minus capital theta is equal to small theta. So what I've written over here. So I can write this down in terms of the angle, the small theta, which is the angle between the incident and the scattered direction. I can write it down. So this is basically then half, okay, r0 squared 1 plus sine squared theta. This capital theta. And this is basically then half r0 squared 1 plus cos squared theta. So your d sigma d omega unfold this, where this theta is the angle between the incident and the scattered radiation. Okay, so now this formula is also important because when you look at scattering, you can think of scattering which are polarized beam coming or an unpolarized beam coming. So this is what happens for unpolarized beam. Okay. So this is practical formula really used. You see there are few things over here. First of all, this theta, as I said. So now the only angle that comes over here is the angle between the incident radiation and the scattered radiation, which is this theta. So that tells you what is your, and which is what it should be, right? Because previously also remember your cross section was something that came in from incident and processed it and went to the scattered. So over here, that is the angle that should come in. So which is this? There are two terms, and these two terms come from the two different directions of the polarized instance. So there's one term over here, another term over here. Okay. So two different directions of the plane normal to n cap. Okay. So if you look at your n cap, the two different directions. That's the two terms. So again, you can look at this thing and make few points. So first point, of course, as I said, is that depends only on angle between the incident and the yes.
Sir, the second light, the second beam is perpendicular to the first the beam direction. That can be understood that one is left circular and another is right circular in that way. But sir, why it is
These
necessary?
Why you're saying left circle is just these are plain polarized.
Okay, okay.
They're not.
But sir, I just want to know, sir, with the direction of n cap, why it necessarily should be at a angle of pi by 2?
No, you think of the, so go back to the previous thing over here. This is simple. This is linear polarized. Okay. This you can try to think in terms of what is your, how when this radiation goes, what is the direction of your E? And you'll see this E, the incident E should be in this plane, and the outgoing E should also be on this plane. There's nothing that will move the.
So n is in the plane of epsilon.
Plane is this is the blackboard or whatever, the screen that you see is the plane, right? So in that plane is an
Okay.
X and n is in that plane. That has to be.
Okay.
You're nothing. Now, over here, I want something where I can define another plane, okay, which is defined by n cap and E2, which is perpendicular to this plane. Suppose I draw a line perpendicular to this plane. Think of, you put a hand on the thing, okay? And there's an n cap. So there's another plane like this. So there will be, can you, I don't know, I cannot, there's a problem. I cannot show you over here. Take a,
Yeah, n cap lies on both of the planes.
yeah, n cap lies on both of the planes. And so,
Yeah.
because n cap lies on both of the planes, the final thing is unpolarized. Because, sorry, the initial thing is unpolarized, because I can always have my two unpolarized thing, two polarized thing like an unpolarized thing. But n cap, when something goes on n cap, your vector is always perpendicular to n cap. That's the way the radiation fields are, right? So the outgoing radiation is always polarized, even when the incident radiation is unpolarized. That's an interesting thing over here. That's one of the points that one should look at. Okay, so first, if you look, turns out that the angle is between only the incident and outgoing. So it was only on the angle between incident and outgoing. That's one thing. Number two, there is a forward backward symmetry. So forward, backward symmetry. So theta 2 minus theta. Okay. Of course, I can write down just the sigma total unpolarized. Okay. That is 8 pi by 3. This is very interesting, that you should convince yourself that this should be the case. R0 square. So you see the sigma total cross section unpolarized is the same as total cross section polarized. Okay, and convince yourself that this should be the case, because the total cross section is basically the total cross section, the total area that beam coming from anywhere faces. So your total cross section should not change. This is exactly the case over here. And the fourth interesting point is that your incident total incident, because we have two polarized, so the total incident I can cancel it. The total incident is unpolarized. But your outgoing is polarized, because again, outgoing has one direction n, and electric vector has to be perpendicular to n. So outgoing is polarized. Okay. So when a polarized thing comes, it gives you a polarized outgoing. When an unpolarized thing comes, it still gives you a polarized outgoing. And you can, in fact, write down what is the degree of polarization. Okay, so you can write down the degree of polarization. So and that typically is called pi. Okay. So the polarized intensity in the plane, and so we'll write down it like this. Before I write it down, let me write it. So when you look at this equation, this tells you that if I take the ratio of the polarized intensity, okay, in plane and the ratio to perpendicular to the plane of scattering, this is basically cos square theta by 1. And so, because it is like this, I can write down a degree of polarization, and the degree of polarization will basically be 1 minus cos square theta over 1 plus cos square theta. Now, cos square theta, of course, goes from 0 to 1. Okay. So your pi is always greater than or equal to 0. So your pi is always greater than or equal to 0, which basically means that the scattered wave always has some polarization. It's never unpolarized. Okay. So scattered wave always has some polarization. Also, when your cos square theta is basically 0, then your pi is 1. So pi is 1, meaning 100% polarization. Okay. When you're looking perpendicular to the incident. So if your incident is K and your observation direction is 90 degrees to it, perpendicular to it, then there is 100% polarization. In any other direction, it is less than 100%, but it is always polarized. So when you're looking at 90 degrees to incident direction. Okay.
Sir,
Yes, Nikhil?
is it because the dipole is radiating itself?
No, again, say your last word I could understand. What was the first word?
Is it because the dipole is radiating?
Yes, of course. Exactly. It is because the dipole is radiating. You can connect it like that. It has the same feature of the dipole radiation. It has this cos square dependence, and your cos square 2 bulbs are like this. Always.
And the EM wave is also getting deflected because of the radiation, right?
For the unpolarized, yes. For the polarized, remember there are two. You have to superpose two waves.
Yeah, exactly. That time you have to superpose the radiative part and the incident wave.
Yeah. Now, when we look at compared to other calculations, these calculations are not very difficult. They're easy calculations, but these are important calculations. Remember, because these are things that we use all the time in scattering. Use in scattering experiments and stuff like that. We measure the scattering. We measure, and then basically from there we can calculate. So basically, you can calculate, for example, over here, as you can see, if I know theta, if I know d sigma d omega, the scattering cross section as a function, I can try to find what is R0 squared. This is a direct scattering experiment to calculate R0 squared. Okay, so now let me go to something which comes as a follow up to all these things that I've been saying. You know, that if there is a electron, in this case, for example, an oscillating electron, or whatever, electron going in circle or any charge, which is accelerating and it radiates. Okay, and so it is radiating away its energy, right? So we have talked about accelerating charge radiating. Accelerating charge can be, as I said, can be anything. It can be something going in circle, or it can be something which is going a straight line but accelerating. It's got a bunch of charges. But even if you look for a single electron, when it's accelerating, it is radiating. So when it is radiating, it is of course losing away its energy. Okay. So once it's losing away its energy, this energy, okay, this radiated energy must come from something. It must either come from the energy that is losing away from the object itself, or it can come from whatever external energy is, in this case is oscillating, external energy is impinging on that object. So if something was just radiating without, it was moving without any external field on it, it will lose energy, and so it will basically go down, right? This is the classic case of your neutron star. The problem that we have, there's it's losing energy, so your spin will slow down. It will basically slow down because its kinetic energy is being taken away by its radiation. Or in this case of this electron on which the electronic field was, it can be that this oscillation is due to the energy that is coming in. So whatever energy is going out is coming from the external energy. Okay. So this problem, where I can think of how your external field is doing some work on this object, okay, and that object is losing energy, this idea of work and energy, this is what is known as radiation reaction. Okay. So because of radiation, there is some reaction back on the system. So the electron is losing energy, something is happening to the electron because it's losing energy. So we're going to start the topic of radiation reaction. But again, we are going to do it in a classical way. We're not going to do it a complete full treatment, which we actually cannot do. So if you think of, let's say, even a charge, an electron, if I want to calculate radiation reaction, then one should actually no more think of the electron as a point particle. You have to think of some electron, some region, and then calculate how one part is affecting the other part. So you have to calculate the force on one part of the electron due to the charge on the other part of the electron, due to the acceleration of the different parts. Okay, and that is not possible over here. So we are going to do it in a simplified way. We're thinking of the whole radiation reaction in a perturbative sense. So it will become clear as we go on. So let me just say what I just mentioned till now. So let us talk about radiation reaction. It's an important and very interesting topic. If some of you will be doing QED later, and when you do QED, it's only when then you will really learn radiation reaction. I mean, before that, it will be always hand waving. Okay, so let us talk about radiation reaction. So the idea is accelerated charges radiate. Okay, so radiate energy, and this energy must come from either the particle energy or the external source, external EM source, okay, which is maintaining the energy. So there is a force on the particle. Okay, there's a force on the particle due to this incident radiation. So there's a force on the particle due to the radiation it produces. Because there is energy, and energy is force work done. So work done basically means force into some work done needs a force. So because the radiation is producing, there's a force on the particle which is acting on the particle. Now, again, as I said, all these things will be done a little heuristically. So we have to think of particle will have some size, and we'll make that size to be the R0 that we defined, and maybe we'll let us set it to 0. So we'll take up some size of the particle. So let the particle, and let us talk about electrons. Maybe are just a charged particle. Let the size of the particle, size of the particle be R0. And later we can set it to 0. Set it to 0 later. We also have to understand what is the regime where radiation reaction is important, because as I said, we want to talk about radiation reaction in terms of some perturbation. Okay, so we want to talk about, so you don't want to suddenly the particle to take away all the energies that it collapses. So whatever it's losing is a little perturbation on whatever is there as a source. Okay, so we want to think of a regime of where we are going to work. So the regime, let us define a regime. So radiation reaction in this regime, reaction can be treated as perturbation. And perturbation on what? It's a perturbation on the motion of the particle. So as I said, the particle is, let's say something is going around, it should not give away so much of energy that it just collapses. So obviously your orbit will change, but it's little change. Okay. Perturbation on the motion of the particle. So if I define, so let T be some time scale over which the kinetic energy of the particle changes substantially. Okay, so T some time scale over which kinetic energy of the particle changes substantially. Okay, and you know what is the power being radiated. So we already know P is equal to your 2 E squared U dot squared by 3 C cubed. This is the power radiated. Okay, and so my time scale, this T, would be approximately, in some sense, your mu squared divided by this. That's the typical time scale. That's how I would say it. So if you have some kinetic energy divided by how much power radiated, So what are these time scale things will change. And so this I can calculate. Okay. So this is equal to 3 mc cube over 2e squared. And there is, so remember this is, so u dot is your acceleration. So over here, I have u by a whole squared. Okay. So this is the time scale in which things are changing. And we want to look at time scales where it's much smaller than this time scales. Now, if I look at your u by a, the u by a, this is the time scales which is the typical orbital time scales, right? So this now, this is a typical period, okay, or orbital or period. Orbital time scale. So what we want basically, we want t by this tp, that should be greater than equal to 1. That's what you want. So it should be many orbits before you have a significant reduction in the energy. We can think of another time scale, okay, for tau. You can think of another time scale tau. This tau is 2e squared by 3 mc squared. Okay, so this is this thing. So see, there is 3 time scales coming over here. There's a time scale which is this, given by this. Okay. Over here we have got another time scale, and this also gives you another time scale. Okay. This is like R0 by C. So typical time scale in which your information can propagate. So as long as the process occurs in a time scale which is much longer than this, see this tau, we can do this radiative reaction, whatever we want to do, perturbative. So as long the process takes much longer than tau, we can treat reaction perturbative. So now when I want to do perturbatively, what I want to do is I want to look at simple energy balance. And over there also we're going to make some very simple approximations. Okay. So let us look at energy balance. So let us look at energy balance. So I will define this radiative force, and then I will calculate what is the work done. So I will define radiative force. So let this be some force. Okay. This is the radiative reaction force. And remember, we are doing it perturbatively. So this is small. This is very important. Okay. And so we're going to define this in a perturbative sense. Okay. So this force is a small perturbation to the external force. Okay. Right. So because we are in the perturbative regime. This F rad, okay, is small perturbation to external force. So that's the simplest assumption. So now I can look at the energy being radiative away, and that energy I will equate it to this force, work done by this force. So energy radiated, this is basically work done by so you know what is energy radiated, which is 2E squared U dot squared by 3C cubed, and this is my F rad dot U, the force balance equation. Okay. Now, one should also understand over here that this equation does not hold instantaneously. Okay. Because then what I can do is that I can always change to a frame where this U is 0 and this will not. So this equation is not hold instantaneously. So when I use this equation, it has to be in some sense of an average equation. So it's going on, take a little bit of time, take an average, and over the average, the work done by this radiative force must be balancing the energy that is. So we need to average over some time. So let's say T1. So when we do that, then that basically means we have to integrate this. Okay, basically we will integrate it, and this T1 to T2. Remember,
Awesome.
Nikhil, yes.
Yeah, why is this not holding instantaneously? I'm not getting that.
Why is it not holding instantaneously? So you see, if you hit instantaneous, then you can always go to some preferred frame, okay, related to which U is measured. And in that frame, I can always make this 0. So on one side will be 0, the other side will not be 0.
Yeah, fine. Sir.
It's always changing, right? And remember this T1, also remember this T1 minus T2. Remember, this has to be this larger than tau. So that you must also, so this T1 minus T2 must be larger than tau, larger than tau. Okay. Okay, so then what we do? So we need to now. So I'm going to integrate both the sides. Okay. So T1 to T2. If red dot U dt is equal to this integral 2 squared by 3C cubed. This is what it is. Now I can do this right hand side integral by parts. Okay. So if I do this right hand side integral by parts, then it becomes 2 squared by 3c cubed. There will be the first part, which is basically T1 dot q T1 to T2 minus integral T1 to T2, where you have a u double dot u. Now, here is when I do the next very simple trivial assumption. As I said, we are doing this perturbatively, and we do not want the system to change that much between, it will change only when it goes to the T large, remember the big T. That's the time scale in which the system changes. The time scale, a shorter time scale, is when the system does not change that much. So between T1 and T2, the system doesn't change that much. So we assume that the initial and the final states are basically the same. Okay. That was an assumption. So as long as T1 minus T2, the system doesn't change. So initial and final states are the same. That's a simple assumption. So every time we're doing assumptions, they're really simple. Which basically means this first term on the right hand side, that drops out. Okay. So the first term right hand side drops out. And so now I can write it like this. Because the first term has dropped out, I can write it as, so minus integral of T1 T2 that minus 2e squared by 3c cubed double dot this dot q. And this tells me, because your UDT is arbitrary, it has to be at different use, this thing should be 0. And this therefore implies that my F red, the radiation force, is equal to 2p squared by 3c cubed double dot.
Sir, all of these are for the non-relativistic case, right?
Nikhil, you have to say it slowly. When you say your first words jumble up and then the second words come.
All
See,
of these are in the non-relativistic case, right?
They're all in the non-relativistic case. All. When you go to relativistic case, all these things become much more complicated. In fact, the radiative reaction is has a huge history in. I'll try to do a little more. Last time I did less. I thought I would maybe do a little more this time. Now, there's a huge history in the building up of electrodynamics. It was first calculated by Lorentz. Okay, so it's as early as that, and it brings out all these questions about what happens when it's a point charge, whatever. All these things about all the problems of the classical case where everything blows up when these are point charges. All these problems are, this all seeps into this, and these things become more complicated when you have relativistic, because some of these assumptions do not hold them. But one thing you should appreciate over here is something we've got something very interesting. You see the force that we have got. Typically, when you talk about forces, all forces are the double derivative of position. So all forces are proportional to acceleration. The radiative reaction force is proportional to the derivative of the acceleration. So that's very, very different. It's a very interesting result. So your F rad, okay, is basically depends not on acceleration like standard force, like standard forces, but on the rate of change of acceleration. So that's very, very interesting, right? So it doesn't depend on acceleration, it depends on the rate of change of acceleration. Okay, so that's one thing. Other thing is,
Sir,
yes, Amit?
sir, in that sense, only the Newtonian force is only dependent on the acceleration. Like Lorentz force also doesn't depend on the acceleration; it depends on the velocity. I mean that.
Yeah, but we never go on to the third derivative of R. Lorentz force is V cross.
Yeah. Okay.
Okay, so this is one interesting thing, and you know, so what has does is basically increase the degree of equation of the particle motion, right? Your general force equals a second degree equation. Now it has become a third degree equation. And this can lead actually to non-physical situations if you are not careful with it. If you are not careful in solving or basically apply your physical intuition, then you can get non-physical situation. So what I suggest is, why don't you try what happens when F is equal to 0. Okay. What happens with this? See what you get. Okay. See what I get. If your F becomes equal to 0. And next day we'll discuss this. Okay. So if your external force, your F is equal to 0, what happens? In this case, when there is radiative reaction.
Sir, there are two type of problems. As per I know, it's either we control the initial thing, then we have a runaway problem, and if I try to make the final things, then we have an
Yes.
initializing problem.
So there will be runaway problem, and you have to see. So you have to basically use your judgment to get rid of the runaway problem. There will be two answers.
Yeah.
Okay. So find it out, work it out. Maybe next day I will talk about this. But this, I mean, for people who have not seen this before, it should be an interesting thing that you have a force which is depends on the third derivative of position and not on the second derivative of position. Next day we will talk a little more on this radiative reaction, and then depending on how much enthusiasm I have, we'll see how much we'll do on radiative. We can do a lot on radiative reaction actually, but I will see how much we can. So that's for today, and we can start on Friday. Yeah. So one of you, in fact, can take a topic about radiative reaction itself applied to electrons, okay? And that will lead to Dirac's paper, famous paper, when he talks about radiative reaction and stuff. So that can be a topic to one of those. Okay, I think I'll stop over here. and will be taken on Friday.
Sir,
Yes, Amit.
sir, do you have a fine NSEM exam like that or just a presentation?
NSEM exam. The NSEM exam is a requirement of graduate board, not my requirement.
Okay.
So last time also I gave a very short NSEM exam. Actually, you should ask last year I gave a 1 hour NSEM exam.
Okay.
So we'll see. If your presentations, if you work hard on a presentation, the presentations are good, then your NSEM exams will be small. But if you are not doing very well in your presentations, then your NSEM exams will be a longer NSEM.
Okay. And sir, can we do in the presentation something outside from the thing that is done in the class, like magnetohydrodynamics or something like that in the from the plasma?
You can choose. Well, I will give you some topics. I manage is one of the topics anyway. I will give you topics, but don't choose. See, what you said was big. Choose something very specific. For example, radiative reaction would be a nice topic for presentation if someone would have done. We are doing it in class because it's a topic where you can discuss what is the problem, you can say something, you can do some, you can work out a little bit, and you can present something in 20 minutes. Remember, it cannot be a very broad topic, it has to be a narrow topic.
Okay.
I'll give you some topics on Friday, and then you can add more topics to it. Okay. Okay, so we'll stop over here. Thanks for